Okay, now we're going to start second order circuits, which is chapter 8 in your textbook. I actually like this first page of this chapter. It has a quote there from the author down there, Charles Alexander. And he says, everyone who can earn a master's degree in engineering must earn a master's degree in engineering in order to maximize the success of their career. And then he says, if you want to do research, state-of-the-art engineering, teach at a university, or start your own business, or something like that, you really need to earn your PhD. I will say that I have told every engineering student of mine since I've been teaching, which is on and off teaching and on and off career engineer, being a career engineer and a career research scientist, I will say that if you only have a bachelor's degree in engineering, then you don't get very good engineering jobs. You don't get design jobs. You get, sometimes you just be a test engineer, that's okay, but you won't be a design engineer. So the interesting, challenging problems that you get start coming when you have a master's degree. There's also a huge financial payoff as an engineer for those who have a master's degree. The pay is significantly more over your lifetime with a master's degree. And of course, if you want to go into research or teach at a university or even starting your own business, the credentials of a PhD really are a good ticket there. But as a minimum, if you've made it through 4 years of engineering school, which is a rigorous curriculum as it is, you also spent half that time doing your general studies courses, you really ought to go on to your master's degree. So I will second the author's quote on here. Strongly second the author's quote on here. Okay, so a second order circuit, as you can guess by now, is going to have a second order differential equation involved, which means a second derivative. So it will consist of resistors and two of our other passive energy storage elements, be it inductors, be it capacitors, or in some way where you cannot lump the elements together, like in the example C and example D. You cannot lump the two capacitors or the two inductors together, so they are separate. They will come up separate when you start writing equations for them, and that will create a second order circuit. So we're going to have two cases to analyze, just like we did in the last chapter. In one case, we're going to look at the natural response of the circuit, so there will be no sources present. So it will have some initial charge on some element in there somewhere, and you will see what happens when you open and close a switch and how the circuit will behave by itself. And then we'll look at the forced response. That means that the sources are present. Missing bracket. Sources will be present in the circuit. We'll need to be very diligent in what are initial and final conditions for these analyses. So initial and final conditions in the circuit will be very important. And additionally, the derivatives of the current, di dt and dv dt, derivatives of the current and derivatives of the voltage will become very important in solving these problems. So the main thing is that we're going to go through a set of rules coming up to find all of these initial conditions, and you have to remember these rules and be very consistent about these rules. So finding the initial and final values in the circuit. So I'm going to spend just like your author does, section 8.2. We're going to just look at examples of finding the voltage and the current at time 0, the dV/dTs, di dTs, and the voltage and current at the infinity time in the circuits. So, unless otherwise stated, V will be a capacitor voltage and I will be an inductor circuit when we look at this section. And the other thing to remember is we must be consistent about the polarities. So a capacitor has a polarity involved in it, and also if you define current in a certain direction, then that is defining where the positive polarity is in that particular segment of the circuit as well. So keep in mind that the capacitor voltages are always continuous. So a capacitor cannot suddenly change current. A capacitor can suddenly change voltage. A capacitor, say that again, a capacitor cannot suddenly change voltage. So the voltage is continuous when the switch is closed or the switch is opened, whatever the case may be in the circuit that we are analyzing. So capacitor voltage is always continuous, and we say, so there's always going to be some switch event here. So the voltage at right after the switch closed is the same as the voltage right before the switch closed. And our switches are always closing at t equals 0 in this chapter. And the inductor voltage is always continuous. So these are kind of complementary elements, but the voltage right before the switch closes or opens will be the same as the current right before the switch opens or closes will be the same right after the event for an inductor. So, and our third little step or rules that we want to particularly pay attention to is that you focus on number 2 first. So as we look at our next circuit and you're saying what happens right at the switch, this is what we're going to be concerned with, and then you get what happens at infinity second. So let's look at the first example. This is an example in your book, and then after that I'm also going to do, because this is such an important section to have a good hold of, I'm also going to do some of the practice problems that they have that they don't give the solutions for, that you're supposed to practice. Well, they give you the answer, but I'm also going to work some of those practice problems for you. So here's our circuit that we want to look at. It says that the switch has been closed for a long time. So if the switch has been closed for a long time, that means your capacitor is going to be fully charged up, and it will be behaving as an open circuit at that point. And that will also mean that the inductor is going to be behaving as a short circuit after a long period of time has happened. So assume that the switch has been closed for a long time. What does the circuit look at then at t equals 0 minus, which is just before we open this switch? And we assume that for an infinitely long time before this event, before the switching event, the switch has been closed. So if the switch has been closed, this guy is a short circuit, and this capacitor over here is an open circuit. And now my circuit will look like, it will be still 12 volts. It'll be 4 ohms there. This is a short. There is still that 2 ohms there. And the voltage where the capacitor is open. So right before this infinity before the switch opens, this is what the circuit looks like. So we can find now remember now the switch is suddenly going to open. So what I can find current in this circuit. So at 0 minus, at that time 0 minus, I will equal what? Just Ohm's law. It's going to be 12 volts divided by 4 ohms plus 2 ohms. Sorry. 12 divided by 6 is 2 amps. So, and then the switch closes. Well, the current cannot change instantly. There is an inductor right here, and the current will not change instantly. So that means that I, which is I in the inductor, at time 0 plus must equal this 2 amps. And it's also, by the way, just equal to I in the inductor at time 0 minus. They are the same. So, see, that's the first one that we get. Okay, so what is V at time 0 plus? Well, at time 0 minus, the V is right here. The capacitor is open. So we can get that. V in the capacitor at time 0 minus is this I times R, 2 ohms. So 2 times 2 equals 4 volts. And that's going to be the same as I in the capacitor at 0 plus. Why is that? I mean V. Sorry, V in the capacitor at time 0 plus. Why is that? Because the voltage on a capacitor cannot change instantly. The current in an inductor cannot change instantly, and the voltage in a capacitor cannot change instantly. So, okay, so we found those first two things. That's part A. part B now, we want to find di dt right after the switch opens. And so what do we know about di dt? We know that C equals, we know that L, I just wrote this down, it's momentary blank, right? We know that C equals dv dt, and we know that L equals di dt. Those are the two things that we know that are derivatives. So di is going to be related to L, and dv is going to be related to C in this circuit. So let's look at what happens. Doesn't matter, we'll do either one first. Oops, I mean, right? I'll pause this for a second. Let me fix. There, I erased my little mistake there. So let's write that again. We know that I in a capacitor equals C dVc dt, and we are wanting to find dV dt at time 0 plus, and we know that the other one that we know is that voltage in the inductor is L, di in the inductor dt. And so the other thing that we need to find is di in the inductor dt. So we know these two things. I'll do this one first. If we have this equation, then we know that dvc dt equals I sub c over the capacitance. Well, we can find I sub c the instant that the switch closes, correct? So that the instant the switch closes, what is the current going here? So we redraw the circuit. We redraw the circuit at the instant the switch closes. And where's my pen? The instant the switch closes, we have the 12 volts still here. We have the 4 ohms there. We have an inductor right there with 0.25 henries. And we no longer, I mean, switch opens. The instant the switch opens is what we no longer have this 2 ohm resistor here because that switch is open. And then we have a capacitor right here that has an initial charge on it of 4 volts right there. So the question is, can we find I in this loop? And yes, we can. It's the I that we just found up here. So that's the current that we have. So it equals 2 amps divided by the capacitance 0.1 farad, and we get 20, and amps divided, the units will be in volts per second. So you can check that. So that is because farads is a volt per farads is a volt. Just check that. Check those units real quick. Because an amp is a joule per second. I mean, yeah, a joule per second. Coulombs per second. I'm sorry, coulombs per second. And a farad is a coulomb per volt is a farad. So this is a, whoops, come on pen. Sometimes my pen disappears, especially when it's late on Sunday night. Why am I not getting my pen back? So a farad is a coulomb per volt, and so amps divided by farads will be a volt per second. So those units are true. So the next one that we need to find, so we have this one. We have actually this one. dV, yes, we have this one right now. We need to find di dt. the instant the switch is opened. So we know that voltage in the inductor equals L di in the inductor dt, and when the switch first closes, the switch looks like this, and we know that we have 2 amps in the circuit right now going this way. That's the current in the circuit right now, and we know we have 4 volts and we have 12 volts, and we can have the voltage right here, and once we apply KVL here, the only voltage remaining is the voltage in the inductor. So we'll do KVL. We have 12 volts equals I times 4 ohms plus voltage in the inductor at time 0 plus the 4 volts from the capacitor. And so we know that I is 2 amps at this time. 12 equals 8 plus 4 plus voltage in the inductor at time 0 plus. And so we get voltage in the inductor at time 0 plus equals 0. Gee, is that right? Yes, it is right. Okay, it has no choice but to be right. I agree it's right. Okay, so we found that one. So all that's left now to find is what's the current at infinity and what's the voltage at infinity. So you go back and look at the circuit. This is our current condition right now, and we know that at infinity this guy is a short. So you had the 4 here. The inductor is a short at infinity, and at infinity this guy is fully charged up to its 12 volts, and it's an open circuit. So I at infinity must be equal to 0 because it's opened at that time, and V at infinity, the voltage on the capacitor, must be back equal to the 12 volts. So it's remembering really to apply the rules on this circuit. So let's do the next example. Coming up right here, next example. So this one, the textbooks gives you the answer but doesn't work the problem out for you. So we'll do that as an example. So let's see, the switch was open for a long time, but now it's closed at t equals 0. So when the switch is open for a long time, you say, what's happened in the circuit? So if it's been a long time, this inductor is a short, and this capacitor is an open, and so at t equals 0 minus, which means that you've been in this configuration for a long time, you now have a circuit that looks like this. A capacitor that's an open, and you have that 10 ohms right there, and you have a short where the inductor is, and you have 24 volts right here. So that's what happened. Just right before we close the switch, the circuit looks like that. And so can we find I at this time? Yes, it looks like a normal application of Ohm's law and KVL. So I at time 0 minus equals I at time 0 plus. And this is the I that we're talking about. I in the inductor right here. So the inductor is a short right now. So then that would just be equal to the 24 volts divided by 10 ohms plus 2 ohms, which is 12 ohms. So 24 divided by 2 is 2 amps. Did I get it? Yes, I did get it. Okay, so then the other thing is what's V, which is V across the capacitor at time 0 plus. So first we look at time 0 minus when we have this circuit right here, and the question is what's the V right here? V in the capacitor right there. So that would be V in the capacitor at time 0 plus would be equal to, it's just an IR thing, so the I that's in this circuit times the R right there. So it would be I times 2 ohms, which equals 4 volts Yes, I got 4 volts. Correct. So that's part A. Part B is to find the rates of change at the instant the switch is closed. So the first thing we have to do is say, okay, let's close the switch. When the switch is closed, the instant the switch is closed, you have a capacitor here with 4 volts across it. And the switch is closed, so if this switch is closed, this 10 ohm resistor goes away because it's shorted out right now. So I still have that 0.4 Henry right there, and my 24 volt source right here. Okay, so this is what happens at the instant the switch is closed, and then we need to find the rates of change. So first of all, remember that voltage in the inductor right here equals L di in the inductor dt, and we want to find that di dt. So we can do that just by application of Kirchhoff's voltage law in this loop because we have known voltages, so we'll apply KVL. KVL says I have, watching my polarities right here, I'm going to have my assumed direction right here. I have 24 volts minus voltage in the inductor minus 4 volts equals 0. So voltage in the inductor must be 20 volts. So now back to this equation right here. 20 volts equals L di dt, and we have L is 0.4 henries, therefore di dt in the inductor at time 0 plus equals 20 divided by 0.4 henries, which equals 50 amps per second. Yes, that's what they got. So let's look at I in the capacitor. The instant the switch closes, well, capacitor can't instantly change current, and right now it's at 0, so the I in the capacitor must be 0, which is the answer right there. But let's just show it mathematically too. So we have I sub C equals C dV dt. Yeah, I was supposed to find dV dt. So let's do that. So this is at 4 volts, but there's no current flowing here. But I can do KCL in this loop. So current into this node equals current out of this node, and prove that there's no current flowing in this node right here. So this was 2 amps. We know we have 4 volts at this node. 4 volts divided by 2 ohms right here is 2 amps. And indeed, there is no current flowing in this capacitor, flowing right here in this part of the circuit. So we have 0 equals C dV dt. Therefore, dV dt equals 0. So that checks. Part C of this circuit. Part C, we have to find what's happening at infinity. So at infinity, we have, this is now an open circuit here, so it goes away. Delete. That one's open, and the other thing at infinity, this guy right here, is now a short circuit. At infinity, here we go, this guy is open, this guy's a short circuit, and infinity, this has still been shorted out by that switch closed. So kind of a trivial problem, but I at infinity, with the circuit now looking like that, is 24 volts divided by 2 ohms, which equals 12 amps. And I only see 2 elements here, so if this is 24 volt source, this must be 24 volt drop. So, and if there's 20 volts right here, there's 20 volts in the capacitor at time infinity also. So Okay, let's do this next example. Your book does it, but sometimes they take shortcuts, and also I saw that the way I thought about the problem was a little bit different than the way they thought about the problem or went about the problem. So sometimes it's nice to have complementary viewpoints. Okay, so the first thing to notice is that this is a source right here that turns on at t=0 by virtue of this step function right here. So for t less than 0, this is 0 amps and it's not in existence in the circuit. So from t equals minus infinity to t equals 0 minus, this is not in the circuit, and the question is what's happening in the circuit at t equals 0 minus. And keeping in mind that certain things are at 0 minus are the same at 0 plus, right? So at time 0 minus, this circuit has been, this part of the circuit has been sitting here for an infinite amount of time, and that means the capacitor is now an open circuit right here. So this is open right here, and at an infinite amount of time, this inductor is now a short. So I was trying to draw a short circuit. Sometimes it's hard to draw on this drawing pad. Whoops, come on. It's a little bit sensitive. So okay, so this one is now a short circuit at t equals 0 minus. So I'm just going to short it out to remind us it's a short circuit at t equals 0 minus. So then what's happening in this circuit? So all you have happening in this circuit at this point in time is you have this 2 ohm resistor, this 4 ohm resistor, nothing right here, and then you have a voltage source right here of 20 volts, and you have a short right here. So the question now is to analyze the circuit the way it looks right here. What do we have happening here? I see no source driving that circuit, so nothing is causing any current to appear in this circuit whatsoever. This is open right now, so that no current can come from here. So this has no current flowing in it. So therefore, this is I in the inductor right here, I in the inductor at time 0 minus, equals I in the inductor at time 0 plus, which must equal 0. Nothing's happening in this circuit. So what about voltage in the capacitor? Voltage in the capacitor at time 0 minus, which equals the same thing at time 0 plus. So what do we see here? We see perhaps that we'll call this our 0 reference place. So if that's at 0 volts, this is a short, so that must be at 0 volts right here. But I went up 20 volts right here, and now I have to be back at 0. Therefore, I must be having to go down 20 volts right here. So I went up 20 volts. This is open, but I got to be back at 0 right here. So therefore, voltage across the capacitor must be minus 20 volts, which also equals, because there's no instantaneous change of capacitor voltage, that's also the voltage at the capacitor on time 0 plus. The other thing we need is a voltage. So we got this one, we got this one. We need voltage across the resistor at time 0 plus. Well, at time 0 plus, this has been turned on, correct? So the question now becomes to analyze the circuit at this point at time 0 plus with that current source in there. Now it didn't matter here, remember, because current can't change instantly in an inductor, so 0 minus and 0 plus current are the same, which would be 0. Voltage can't change instantly in a capacitor, so voltage at time 0 minus and voltage at time 0 plus are the same. However, this 3 amp source has now turned on, so that means that other things could be happening part of the circuit that's not in this part of the circuit. So what do we have? We can write KCL at this node right here. I'm going to call this node R because it's related to, it's the voltage right here, VR, and for analysis purposes I'm going to call that point node C. So we want VR, we need to find VR. So if we do KCL at node R, we get that 3 amps goes in, keeping our current conventions this way. since this is a voltage drop here, current needs to go that way. That's our convention. And I chose to make this one this way, even though I don't really know, just because I have IL defined in this direction also. But I suspect that this is also going to be a voltage drop. It just makes sense. So anyhow, so 3 amps goes in, and then we have voltage in across R divided by 2 ohms plus. Now, if this is at 0 volts and this is a short at time 0 plus, then this is also at 0 volts. So we have the same voltage here, right? So it's also going to be a VR over 4. And so now I do my algebra, and I will come up with that VR equals 4 volts, and that is V at time 0 plus. Okay, so that's 4 volts. That's 4 volts, that's 0, and that's 0. That's what we've found out so far. Now we need to find these rate of changes over here, part B. And we know that our rules, voltage in an inductor equals L dI in the inductor dt, and current in the capacitor equals C dV dt. So these are the things that we know. So let's look at this one first. We did know that okay. So current right here at time 0 plus was 0, and this was a short, right? Because after infinity time, this is a short circuit right here. But yet we had that no current was flowing by virtue of looking at the circuit. So, but anyway, the fact that that's a short circuit implies that voltage in the inductor at time 0 plus must equal 0. If that's a short circuit at 0 plus, then there must not be any voltage right there, right? So therefore, if I just plug that back into this equation, dI dt equals voltage in the inductor divided by L, which is 0 divided by L, which is 0. Okay, so that takes care of that. So now let's look at the capacitor one. What do we know about I sub C? So current can change instantly here, right? What do we know about this right now? Well, we know that voltage at that time period, but we don't know what the rate of change of current is, because this capacitor starts doing something as soon as this circuit is turned on at time 0 plus. So let's apply KCL at this node C, KCL at node C, and see if we can determine what this rate of change of current is going through here. So we did have that 4 volts, and we had 4 volts here and 4 ohms, so we can find out what that current is right here. So 4 volts divided by 4 ohms, that's that current going into the node, and let's say going out of the node is I sub C at time 0 plus I sub L at time 0 plus. So we have 1 amp equals I sub C at time 0 plus I sub L. And I sub L at time 0 plus we already figured out was 0. So therefore I sub C at 0 plus equals 1 amp. And now we go back and we substitute into that equation right there. 1 equals C dVc dt. Divide both sides by C. C is half a farad. And we come up with the Vc dt equals 1 divided by 0.5, which equals 2. Units are amps per farad, which an amp is equivalent to a coulomb per second divided by a Coulomb per volt. So those units do indeed equate to volts per second. So there we found those values. What am I missing? So I got this one, and oops, I need the rate of change in the current across the resistor. So rate of change of current across the resistor. I had to pause for a second and move stuff onto the next slide because it was getting too crowded. So I transferred to the next slide here. Here's where we were at. We were here right now. We found these values so far, and now we need to find dVr, which the change of the voltage, rate of change of the voltage across this resistor as a function of time. So I transferred the values that we have found so far, and the question now is that we have to find dVr at time 0 plus. So we need to find the rate of change of the voltage at that node right here. So, oh, it looks like a node equation, so I'm going to do KCL. So I'm still on part B right now. I'm going to do KCL at node R, because I called that node R, and I'm going to do it at t equals 0 plus. That's where I'm at right now. So we have current going in, current going that way, current going that way. We have 3 amps goes in equals VR, this voltage right here, VR over 2 ohms. I mean that current right there, VR over 2 ohms. And the other part that's a little bit tricky is what is this current right now? It's VR. It's well, the resistor, you're going to divide by the resistance, and then the voltage across this resistor right here. So I'm going to divide by the resistance, so that's 1 over 4 at 4 ohms. But the trick is that the voltage here now at this point of time is VR, and this was my other node, minus VC, because we know VC, we have a value for VC, the rate of change of voltage right here. It's no longer some instantaneous, I mean right at 0 plus, this was at minus 20 volts, but it does have a rate of change that's, which is actually at 0 volts there. It does have a rate of change of voltage now going forward. So this is where the trick of the equation is right here, or the thing that you have to realize. So that's really my KCL at that node. So I'm going to go ahead and rearrange the terms a little bit, combine the VRs right here, so that becomes 3/4 VR minus 1/4 VC. So I'm interested in the rate of change of the voltage R, so that means I need to take the derivative of both sides. So I'm going to take the derivative of both sides with respect to time. I'll just do it that way, take the derivative. So derivative of a constant is 0, and that will be 3/4 dVr dt minus 1/4 dVc dt. So dVc dt we have a value for. So 0 equals 3/4 dVr dt minus 1/4, and we have a value for that. It was 2 volts per second. So now we can go ahead and find, just from the algebra, dVr dt at time 0 plus, then equals, just from the algebra, will end up be equal to 2/3, 2 over 3 volts per second. So that's 2 over 3 volts per second. So these dVs, dTs, V in the numerator, T in the denominator, will always be in volts per second. So now we found that one. Now we just have part C to do. What happens at time equals infinity? So time equals infinity means that this is an open circuit now, and this is a short circuit, and you redraw the circuit that way. I will again make this a short circuit. I will again make this an open circuit. And so the question is, what does the circuit now really look like? It really looks like this, with 2 ohms there, 4 ohms there, and that's a short. This is definitely a circuit we can analyze under our ordinary techniques, but once again, V across the capacitor at time infinity, right here, we came up 20 volts, we go down again, so that's going to be again at minus 20 volts. I in the inductor, right here, IL, we don't know yet, it's a short circuit, but we can analyze that, right? And V in the resistor, that's we can analyze that just by virtue of doing an ordinary analysis of the circuit. So we can do it this way, I guess. 3 amps equals VR over 2 plus VR over 4, and again we get that VR equals 4 volts once again. So VR at infinity must be equal to 4 volts. So, and then we need I in the inductor. Well, we have 4 volts. 4 volts divided by 4 ohms right here for the current in that leg right there, which is 1 amp. Okay.